Okay, as review, we're going to talk about computing the length of curves in 3D. Because I'll show you a slightly different way to do it than you might be used to. So in 3D, we could write z as a function of x, and we could write y as a function of x, but this is kind of, it's actually a lot harder to do this. So really what we use is we use t, right? And so we write r as a function of t. It's a vector function. And objects like this are much more useful to integrate than graphs. In this case, we would have had this graph x, y of x, z of x, and this is a little uglier. And so how do you actually get the length from these vector functions? Well, again, you split it up into, so you split the curve into lines. And then you calculate the area for each line. Really, these are segments. And then 3, you add all the small areas. Or rather, not areas, we're still in 1D. This is just a, I'm reviewing this because we're going to move to areas, and this situation is a little easier to see. So if we split this up into line segments, like so, and of course we get more accurate as the grid is refined, then how do we actually calculate the area of one of these things? Because, for example, this is r naught, r sub 0. If this is r at a particular time, then here's going to be r at t plus dt. And so this displacement vector, delta r, this is what we'll be using the length of. So the length is equal to the length of our displacement vector. And it turns out this thing, it's r of t plus delta t, I guess we're using dt, minus r of t. And so by Taylor expansion, or mean value theorem, we know it's r prime of t times dt plus a higher order term, which we'll neglect as dt goes to 0. So this is just the length of r prime of t dt. So in other words, the length, we get it by computing the derivative of the vector function, and then we integrate, right? Because then the total length is just the integral of the small lengths. So it'll be the integral of r prime of t dt. So the idea is we get some, notice this has dimensions of meters, right? Meters per second times second. So it's the right dimensions. So for area, we'll be getting a double integral of, you'll have eventually 2 r primes, because remember we need to have dimensions of meters squared, and then we'll have something like dt squared. It won't be this, but that's the idea, because that'll give you meters squared per second squared times second squared. And area, of course, has meters squared. So it's just that we need to find out what exactly these things are, and that'll be the subject of my next video. Thanks for watching.